Next chapter, surface area of solids. Surface area of prisms. Prisms are solids that have uniform cross-section. They are named according to the shape of the cross-section. That said, this is a triangular prism. A cylinder is a circular prism. This is a trapezoidal prism, and a cuboid is a rectangular prism. Surface area is the total area of all the faces making up the solid. We start with the cuboid. A cuboid has 6 faces, and so we will work out the area of all the faces and add them up together. We have a rectangle at the front with a length of 4 and a width of 3. And there are 2 of them. Then there is a rectangle on the side, and of course on the solid it looks like a parallelogram. And there are 2 of them. Then the top rectangle and the bottom one, and they measure 2 by 4 centimeters. So now we calculate the area of all these faces and add them up. All are rectangles, and so area is length times width. So this is 3 times 4, that gives us 12, and there are 2 of them, that makes it 24 square centimeters. Then these blue ones, 2 times 3 is equal to 6, 2 of them makes it 12 square centimeters. This is 4 times 2, that is 8 square centimeters, but there are 2 of them, and that makes it 16 square centimeters. And so the total surface area is 24 plus 16 plus 12, and that gives us 52 square centimeters. Next, we look at the triangular prism, and again we will separate all the faces and calculate the area separately, and then we add them up. It has this triangular cross-section. 2 triangles, they have a height of 10 centimeters and a base of 9 centimeters. We have these 2 rectangles, length 11 centimeters and width 12 centimeters. Lastly, another rectangle with length 11 centimeters and width of 9 centimeters. And now we can start. Area of the triangles, a half base times height, that's a half times 9 times 10, and there are 2 of them, and that gives us 90 square centimeters. These green rectangles, 11 times 12, and there are 2 of them, and that gives us 264 square centimeters. And lastly, this pink rectangle, 9 times 11 gives us 99, and it's only one of it. And so total surface area is 90 plus 264 plus 99, and that gives us 453 square centimeters. And then we go to the trapezoidal prism and do the same. We separate the faces. Trapezia making the cross-section, 2 of them. 1 base rectangle, a top rectangle, and 2 equal rectangles. This is 8, this is 4, this is 9, and length 8. The base is 13 by 8 centimeters. Trapezium is 13 at the bottom and 9 at the top. Okay, now we calculate the areas. This blue rectangle, 8 times 9 is 72 square centimeters. This is 4 times 8, and there are 2 of them, gives us 64 square centimeters. The trapezium area is a half a plus b times height. That gives us a half. 9 plus 13 times 10, and there are 2 of them. That gives us 220 square centimeters. Lastly, the yellow rectangle, 13 times 8 gives us 104 square centimeters. Total surface area, 72 plus 64 plus 220 plus 104 gives us 460 square centimeters. Next solid, cone. The solid obtained by rotating a right-angled triangle about one of its sides other than the hypotenuse is called a cone or a right circular cone. A cone is a pyramid with a circular base. AB is the perpendicular height edge of the cone. BC is the radius r of the base of the cone, and AC is called the slant height L of the cone. According to Pythagoras' theorem, h squared plus r squared is equal to L squared. The total surface area of a cone is equal to the area of the curved surface plus the area of the circular base. The curved surface area of a cone is obtained from the sector of a circle. We have learned about the sector of a circle. A cone is formed by bringing 2 radii so that they coincide with each other side by side. Consider this cone with a slant height L and a base radius r. The circumference of the base is given by 2 pi r. When the cone is cut open, it forms a sector of a circle. The sector formed has a radius equal to the slant height of the cone, L. The length of the curved surface, or the arc length, is equal to the circumference of the base of the cone, 2 pi r. Curved or lateral surface area of a cone is equal to the area of the sector, which is a fraction of the area of a circle. The arc length is also a fraction of the circumference of the circle. This fraction will be 2 pi r over 2 pi l because the full circle will have a radius L. Lateral surface area is equal to arc length over circumference times the area of the circle. That is 2 pi r over 2 pi l times pi r squared, and that gives us pi rl. And so the curved or lateral surface area of a cone is given by surface area is equal to pi rl. For a closed cone with a base surface, when this cone is cut off, it forms a sector and a circle. Total surface area of the cone is therefore equal to the lateral surface area plus the area of the circle. That is pi rl plus pi r squared. Factorizing pi r, surface area is equal to pi r into L plus r. Let's take an example. A circular piece of aluminum sheet of radius 2.1 meters is cut into a sector with an angle at the center of 60 degrees. The sector is then folded into a conical container and filled with water. Calculate A, the base radius of the cone formed, B, the perpendicular height of the cone, C, the surface area in contact with water. In our solution, so this is the sector we are told about. Radius is 2.1 meters. It is folded into a cone. And now we need to know the radius of the base. For us to be able to know the radius, we need to know the circumference of the base. Look at the folding again. In this sector, the curved length PQ is called the arc line. If you look at the folding, you will notice that the arc length is the circumference of the formed cone, right? So we just need to find the arc length PQ. Remember, arc length is given by theta over 360, 2 pi r. 60 over 360 times 2 times pi times 2.1 will give us 2.2 meters. So the circumference of the base is 2.2 meters. Now we can find the radius. Circumference is given by 2 pi r. If we equate 2 pi r to 2.2 and solve for r, we'll find r is equal to 0.35 meters. B. The perpendicular height. Look at the folding once again. You realize the radius of the sector becomes the slant height of the cone, L. So we have 2.1 meters here. If we draw these lines here, you will notice that a right-angled triangle is formed, and from Pythagoras' theorem, L squared is equal to h squared plus r squared. Therefore, h squared is equal to L squared minus r squared. If you solve that, h is equal to 2.07 meters. C. The surface area. The surface area in contact with water is the surface area of the curved surface since the cone is open. So that is given by pi rl. If we calculate that, we are using the radius of the cone and not of the sector. So we shall have pi times 0.35 times 2.1, and that gives us 2.31 meters squared. Next, frustums. A frustum is obtained by chopping off a cone at a given height above the base. This also results in formation of a smaller cone. An important thing to know is that the smaller cone obtained is similar to the original cone, and therefore the ratio of the sides is proportional. Consider a large cone of radius r capital, perpendicular height h capital, and a slant height L capital. This is chopped off to obtain a smaller cone of base radius r small, perpendicular height h small, and a slant height L small. It follows that r capital over r small is equal to h capital over h small and is equal to L capital over L small. If you remember in similar figures, we call this linear scale factor. If you square the linear scale factor, you obtain the area scale factor. And so if we know the area of one of the cones, we can find the area of the other. So r capital over r small squared times the area of the small cone is equal to the area of the large cone. Or r small over r capital squared times the area of the larger cone will give us the area of the smaller cone. The same will follow for slant height. I'm using the curved surface area only because the cone may or may not be closed at the base. If closed, we calculate the area of the circle separately. The surface area of the frustum is equal to the area of the curved surface plus pi r squared plus pi r squared if it is closed both at the top and bottom. The curved surface area is equal to the area of the big cone minus the area of the small cone. Let's take an example. Calculate the surface area of this hollow lampshade. This is a frustum, but we are told it's hollow, so we only need to calculate the area of the curved surface. We apply the concept of similarity. Before it was chopped off, this was the original cone. The top radius of the frustum is of course equal to the base radius of the smaller cone, 3 centimeters. It is important you see that 5 centimeters is the perpendicular height of the frustum and not the larger cone. Because surface area is equal to pi rl, we need to find L, the slant height. So what we do is first find the height of the larger cone and then use the Pythagoras theorem to find the slant height. Let's have the height of the small cone as h small. From similarity, r capital over r small is equal to h capital over h small. But then, h capital is equal to 5 plus h small. I hope you can see that. So we have 6 over 3 is equal to 5 plus h over h. 6h is equal to 15 plus 3h. 3h is equal to 15 and h is 5 centimeters. And so if h is 5 centimeters, then h capital is 5 plus 5, which is equal to 10 centimeters. Now we can find L. From Pythagoras theorem, h squared plus r squared should give us L squared. 10 squared plus 6 squared, that's 100 plus 36, will give us 136. Therefore, L is the square root of that, and that is 11.66 centimeters. We need the slant height of the small cone. We can use the Pythagoras theorem, h squared plus r squared is equal to L squared, or use the ratios, h capital over h small is equal to L capital over L small. Either will give us the same answer. And so using Pythagoras theorem, 3 squared plus 5 squared is equal to L squared. 9 plus 25 will give us 34. Square root of that will give us 5.83 centimeters. Alternatively, we use the ratio method. 10 over 5 is equal to 11.66 over L. 10L is equal to 58.3 and L is 5.83. The same answer. The curved surface area of the large cone is given by pi r capital L capital. That is 3.142 times 6 times 11.66. That gives us 219.81 square centimeters. Then the curved surface area of the smaller cone is equal to pi rl. That is 3.142 times 3 times 5.83. And that gives us 54.95 square centimeters. Curved surface area of the frustum is equal to the difference between the two areas. 219.81 minus 54.95 will give us 164.86 square centimeters. An alternative method, when we go to the area of the large cone, we could have used the area scale factor to find the area of the small cone. The linear scale factor is L small over L capital because we are going from the large cone to the smaller cone. Area scale factor is equal to 5 over 10 squared. And so 5 over 10 squared times 219.81 should give us the area of the smaller cone. 5 over 10 is 1 over 2. Square of that is 1 over 4. We multiply that by 219.81 and we get 54.95 square centimeters. The same answer we got. Another example, this is a frustum, but now suppose we turn it over and say it's a bucket. We can find the surface area. Common sense will tell you that a bucket is open at the top, so we need the surface area of the curved surface and the small circular bottom. If this is 21 centimeters, this is 14 centimeters, and the slant height is 18 centimeters, we can find the surface area. We start with the curved surface area. Now imagine the original cone. This would be the slant height L. We find the entire slant height L capital. From similarity, R small over R capital is equal to L small over L capital. But then L capital is equal to L plus 18. And so 14 over 21 is equal to L over L plus 18. Cross multiplication. 14L plus 252 is equal to 21L. Minus 7L is equal to minus 252. L is 36 centimeters. And so the slant height of the entire cone is equal to 36 plus 18, and that gives us 54 centimeters. The curved surface area of the larger cone is given by pi RL capitals. 22 over 7 times 21 times 54 will give us 3,564 square centimeters. Curved surface area of the smaller cone is pi RL. 22 over 7 times 14 times 36 will give us 1,584 square centimeters. Now the curved surface area of the frustum is the difference between the two. 3,564 minus 1,584 will give us 1,980 square centimeters. But remember, the bucket has a circular base. Area is pi r squared. 22 over 7 times 14 squared will give us 616 square centimeters. And so the total surface area is 1980 plus 616, and that gives us 2,596 square centimeters. Now, there is another method for calculating the surface area of a frustum, but it may not be very common in textbooks. Consider a frustum with base radius r capital, top radius r small, height h, and slant height L. The surface area of the curved surface is given by pi L into r capital plus r small. Notice that L here is the slant height of the frustum and not the entire original cone. If L is not given, it can be calculated using this relationship. L is equal to square root of h squared plus r capital minus r small, square of everything. If the frustum is closed both at the top and bottom, then we also add the surface areas of the circles. And so the total surface area of a closed frustum is given by pi L into r plus r plus pi r squared plus pi r squared. Let's try that with the bucket. We had been given L, and so we don't need to calculate it. We only have the small circular base, and so the total surface area will be pi L into r plus r plus pi r squared. 22 over 7 times 18 into 21 plus 14 plus 22 over 7 times 14 squared. The curved surface area will be 1,980, and the area of the small circle will be 616 square centimeters, the total of which is 2,596 square centimeters, the same area we had obtained. Next, solid pyramid. This is a square pyramid. Square because the base is a square of sides 12 centimeters. The other surfaces of a pyramid are always isosceles triangles. The distance from the center of the base to the apex is called the perpendicular height. The surface area of the pyramid is calculated by adding the total areas of all the faces. When the pyramid is opened up, this is what we obtain. This is the net of the pyramid, and so we find the areas. Triangles. Area is a half base times height. A half times 12 times 8, and there are 4 of them. That will give us 192. The square, 12 times 12 gives us 144. We add the 2 and we get 336 square centimeters. Now, the base of the pyramid could also be a triangle. So this is a triangular pyramid. The surface area is calculated in the same way. We find the area of all triangles and add them up. The base is an equilateral triangle of sides 10 centimeters. Using Heron's formula, S is equal to 10 plus 10 plus 10 over 2, which gives us 15. The area is equal to square root of 15 times 15 minus 10 times 15 minus 10 times 15 minus 10. That gives us 15 times 5 times 5 times 5. That gives us 1,875. Square root of that is 43.3. And so the area of the base is 43.3 square centimeters. The other 3 triangles, area is a half base times height. A half times 10 times 12, and there are 3 of them. That gives us 180. If you add the 2, we shall get 223.3 square centimeters. Similarly, when a pyramid is chopped off at a given height above the base, we obtain a frustum. Again, the larger pyramid and the smaller pyramid are similar. Also, notice that the sides of the frustum are trapezial. The last solid, sphere. We will perform a procedure that will help us understand the surface area of a sphere. Consider a sphere having a radius r units. We roll a thread around the surface of the sphere without overlapping or spacing between the threads. Now we arrange the threads used in covering the sphere in form of circles having the radius equal to the radius of the sphere. You will notice that the thread used for covering the surface of the sphere is equal to the sum of the areas of 4 circles of the same radius. And so the surface area of a sphere is given by the formula surface area is equal to 4 pi r squared, where pi r squared is the area of a circle.
One of the wonderful things about mathematics, I think, is that people are impressed. It's often seen as a very hard subject, and so if you've done math, it's often treated as an entrance requirement, as a credential to do lots of other things. And so one idea is that for example, some MBA programs, the only thing they require going into it is a good, solid math understanding. They can teach you all the business. They just can't teach you the math fast enough. And so I think that math, aside from obvious careers that require math, if you're going to go work in a department that does operations research or something like that, they'll want people with specific skills in mathematics. But math is often seen as as a filter, as a screen for many, many other disciplines. And so if you, I guess what I'm trying to say is you can think broad because math actually is a solid preparation. It's a good credential to go into lots of different fields that people often don't consider at the beginning.